Hi students, today we're looking at a new side of calculus. We spent a lot of time looking at rates of change and derivatives, and today we're looking at what happens if you begin to accumulate small amounts of change and how we measure that. And this is going to introduce these things called integrals, which is the second big piece of calculus that we're looking at. Actually, I guess it's the third. If you count limits, it's the first. All right, so we're going to start off with kind of a thought experiment, and it's probably helpful if you, sorry, this keeps wiggling, if you were to pause this, find the area of this, and take a look at maybe some similarities between these two. So if you want to pause for a second, I'm going to ask you to do that a couple times today. Try that and then come back to this. Okay, so we've got a couple of different areas to find. The first area is just of a triangle. We've got 4 across, 4 up. We know that area of a triangle is going to be 1/2 times base times height. And when we do that, we get 8. Getting more accurately, we can break this into 2 pieces. And I guess these are not the same, but they could have been. So I guess if we break this into 2 pieces, that makes it a little bit weird for us. Okay, so at 1, oh, what's the height here? That's x cubed. 1 cubed is going to be 1. Okay. And at 2, this is going to be 2 comma 8. So we've got a triangle here. That's going to be 1 across, 1 up. So that would be an area of 1/2. And here we've got a trapezoid. Here we've got a base. Here we've got a second base, and that makes this the height, which is kind of weird. So for a trapezoid, we find the average of the 2 heights. So that would be 1 plus 8 is 9. Divide that by 2 and multiply that by that height. And that height is going from 1 to 2, so it's just 1. So we get 9/2 for that part. That gives us a pretty good estimate for the area between 0 and 2. That's under this curve, but it's a little bit over because we got these weird chunks that are sitting on top here. To make this more accurate, we would need to divide this into smaller pieces. Okay. The next piece of this is going to be on Desmos. And this is going to be linked in Google as something called Riemann Sum Introduction. Once you're finished with that activity, please come back to this video, and we're going to use the skills that you practiced in there. Welcome back. So we've had some practice doing things called Riemann sums, and here we're talking about a model train and trying to estimate the total distance traveled, so an accumulation of this rate for the amount of time that's going on here. This is a little bit tricky because this table is vertical. We've got kind of x values and y values to consider. And thinking about this, I want us to think about the earlier ones are the left side, the later ones are the right side. All right. So to do 10 subintervals of length 1 with left endpoint values. So we're looking at going from 0 to 1. That's going to have a width of 1. And the left side of that interval, we said left was the top, is going to be 0. So it'd have a height of 0. The second interval is going from 1 to 2. So that would also have a width of 1. And the height is going to be the left side of that. That's going to be 12. The third interval is going from 2 to 3. That's a length of 1. I feel like these are all going to be lengths of 1. And the height on the left side is going to be 22. For the next one, we're going to have that 1 again, going from 3 to 4, and a height of 10. And then 1 times 5 plus 1 times 13 plus 1 times 11 plus 1 times 6. And just to kind of clarify, That was the interval from 7 to 8. For the interval from 8 to 9, we're going to have a height of 2. For the interval from 9 to 10, we're going to have a height of 6. One of the things that happens here is that when we're using left sums, we don't end up using that last point on the right. The same is going to be true when we use a right sum. We're not going to end up using that last point on the left. So coming from the right side, we're going to use 0, 6, 2, 6, 11, all the way up until we get to 12. So just to kind of take a look at this, that's going to be 1 times 0 plus 1 times 6 plus 1 times 2 plus 1 times 6 plus 1 times 11 plus 1 times 13 plus 1 times 5 plus 1 times 10 plus 1 times 22 plus 1 times 12. Okay. Most of the problems that we look at are not going to have 10 pieces. This is kind of an exception rather than the rule. The last piece of this is we're looking at 5 subintervals of length 2 using what we call midpoint values. So my subintervals are going to be from 0 to 2, from 2 to 4, I like how I said 2 to 4 and then to 5, 2 to 4, 4 to 6, 6 to 8, and 8 to 10. For the midpoint values, we use the middle of those intervals as our heights. So at each of these odd numbers, because those are the middles of all of the intervals, we can see that we have heights that those match up with. So in looking here, we end up with, for my first interval from 0 to 2, that's a width of 2 and a height of 12. Going from 2 to 4, that's a width of 2 and a height of 10. Going from 4 to 6, that's a width of 2 and a height of 13. Going from 6 to 8, that's a width of 2 and a height of 6. And from 8 to 10, that's a width of 2 and a height of 6 again. This would be my midpoint Riemann sum. That stands for midpoint rectangular approximation method. This would be my RRAM, right rectangular approximation method, and my LRAM, left rectangular approximation method. I'd also like you to notice a couple of things. The first is that I showed all these multiplications even when it was just 1 times that. That's really important for the AP test. You have to show that you know that you're adding up a bunch of rectangles. The second thing is I didn't actually add up any of these things. These are places that it's really easy for us to make some arithmetic stuff. If I can see that you're setting up the Riemann sums correctly, that's what I'm really looking for in this class. Looking at a second one of these, notice how it's way fewer intervals. We're again estimating distance based on right and left endpoint with 5 subdivisions, and we've already got 5 subdivisions for this. So let's do LRAM first. Here's kind of my X and my Y in terms of our lengths and our heights. Another way to think about this is that we've got a time multiplied by a rate that gives us some kind of a distance. Ooh, I also had some fun things going on with LRAM there. That's cool. Okay. So let's do the LRAM. The first interval is going from 0 to 12, so it's a length of 12. And I'm going to use the left side, so a height of 30. Then we're going from 12 to 24. That's a length of 12. And the left side is 28. Then we're going from 24 to 36. That's a length of 12. And the left side is 25. And then we've got 12 times 22. And 12 times 24. That's my LRAM. Looking at my RRAM, we're going from 0 to 12. Oh, the widths are all going to be the same for this. And I like starting on the right side just so I know what's going on. So we've got 27, then 12 times 24, 22, 25, and 28. So 12 times 22, 12 times 25, and 12 times 28. And again, I'm not going to simplify these. I will talk about the units for this. So if we're multiplying seconds times feet, we get feet as a unit. That's really important as well. And again, this tells us the total distance traveled between time equals 0 to time equals 60 based on this data. This is an estimate. This is not an exact value. And that's going to be something that we can't really figure out using rectangles unless we were to get them really, really tiny so that we couldn't actually see the difference between them. The last part about this asks about midpoint approximation. And I'm going to look at this. So for midpoint approximation, we know we need to get into the middle of intervals. So I could go from 0 to 24, and from 24 to 48, and then, oh, I can't do a third interval. So we can't actually use midpoint here because we end up with an issue with trying to make a third interval. Midpoint needs a really specific set of things to actually work. And in terms of that, that's just trying to get things to make sure that we line up with the right number of pieces. All right, one more example. And here we've got oil leaking out of a damaged tanker. And we've got increased leakage each hour. So in other words, we would call this some kind of an increasing function. Thinking about this in this way, if we're making rectangles based on this, if I'm to do a rectangle from the left, it's going to be an underestimate. And if I do a rectangle from the right, it's going to be an overestimate. And that's because this thing is increasing because it's getting worse over time. Looking at this, we're trying to come up with an estimate for 5 hours. So if we want an upper and a lower estimate, we're going to use different types of rectangular approximation. So for an upper estimate, I want to use my over estimate. That's going to be my right Riemann sum. And we're going from 0 to 1, which is a width of 1. And using the right side, that's going to be 70. Going from 1 to 2, and that's going to be a width of 1. And the right side is 97. Going from 2 to 3, that's a width of 1 with a right side of 136. And from 3 to 4, we've got 1 times 190. From 4 to 5, we've got 1 times 265. That's my upper estimate. For a lower estimate, we're going to use our LRAM, and that's because we know that's an under approximation. And we're going to do the same type thing. So we've got a width of 1, this time using the left piece, times 50. Then we get 1 times 70, 1 times 97, 1 times 136, and 1 times 190. So we've got an upper estimate and a lower estimate. We know that the RRAM has to be an overestimate and the LRAM has to be an underestimate, but we don't know exactly what that situation is. I'm going to skip part B, which asks you to do the same thing, but for 8 hours instead of just 5 hours. Last thing I want to talk about is since we're multiplying an hour times a gallon per hour, this estimate is going to be based on the total number of gallons that are escaping.